the least and greatest value of forces. Okay, Umar, have you looked at the, Walaikum Assalam, Bilal. Have you looked at that video that I posted? So I'll show you that concept here as well quickly. You haven't looked at that? Okay. All right. So what I'll do is I will show you a couple of questions like that, and we could talk about that. Okay, let's start with this then. Let's begin with this. So first of all, the least and greatest value of forces that you have to find out sometimes. There are two types of problems that come on that. Okay, there are two types of problems that come on that. One type is, let me just open that here as well. Yeah. This is what you need to remember for that. One type is when you have a rough surface that has friction. Okay, you have a rough surface, so it could be an inclined surface, it could be a horizontal surface, but it's some rough surface on which you have an object that may be moving, or that may be in equilibrium, mostly in equilibrium. In fact, it's not moving generally, it's in equilibrium. And what you have to do is you have to find the least or greatest value of some force. Okay. What you have to do in such problems is you have to consider the limiting equilibrium case. Okay, the limiting equilibrium case. So for example, you might have something like this. Let me show you a couple of questions like this. For example, least possible value or greatest possible value. Let me see if I can find one such example here. Okay, so in this case, it's not exactly a force, but they're talking about the least possible value for the coefficient of friction, right? That's what they're talking about. Now, whenever you have something like this, and you have a surface involved, a rough surface involved, what you have to do is consider limiting equilibrium. That's all that you have to do in every single case like this. When you have a rough surface, then you have to find greatest possible force, least possible force, consider limiting equilibrium. When you consider limiting equilibrium, what happens is you say F equals mu r. That's one thing that happens. Friction is at its maximum value in limiting equilibrium. And the second thing that happens is whatever equilibrium case you have, you say if the object is just about to move down the plane, friction would act up the plane. And if the object is just about to move up the plane, friction would act down the plane. So sometimes you have to consider one of these cases, sometimes you have to consider both of these cases. But that's something that you always have to do in problems like these. Least value of something, greatest value of something, and you have a rough surface involved, consider using limiting equilibrium in those cases. Okay. Now, this is one such example. Have a look at this question quickly. Look at the question statement. Read the question statement. What they're asking about at the end is find the two values of t for which the ring is in limiting equilibrium. Essentially, they're asking for the greatest possible value of t. So sometimes this question is worded like this: find the two values of t for which the ring is in limiting equilibrium. The same question could be worded slightly differently as well. So they might have asked you, find the greatest possible value of t for this particle, for the ring, to remain in equilibrium. This could be another statement that you could get in this case. Now, what's happening is you've got this force T that's applying here. Now, if this force T was very big, what happens is, what would happen would be that the ring would eventually start moving upwards if this force T was too big. So what's the greatest possible value of T for the ring to remain in equilibrium? You would say, let's consider the extreme case, that the ring is just about to start moving. What would that case be? That the ring is just about to slide upwards. So you would say it's in limiting equilibrium with the ring about to move upwards. This case, you would make a case like this. And that will give you the greatest possible value of T, right? Then sometimes they ask you for the least possible value of a force in this case, for instance. Least T for the ring to remain in equilibrium. Again, the ring is in equilibrium right now. If this force T was too small, what would happen would be, because of the weight of the ring, it would start sliding downwards, right? What's the smallest possible value of T for the ring to remain in equilibrium? If you have to find that, you would say, consider the limiting equilibrium case, the extreme case of equilibrium, such that the ring is just about to move downwards. And that will be the extreme case that will give you, okay, if tension was to, if this force T was to even be slightly less than that amount, the ring will start moving downwards. So for the ring to remain in equilibrium, what's the least possible value of T? How would you find that? You would say, consider limiting equilibrium such that the ring is just about to move downward. So this same question, you could get the same answer for this if they had worded it differently like this: find the greatest value of T, find the least value of T. You would say greatest value of T is when you consider the case when the ring is in limiting equilibrium and about to move upwards. That gives you this force T. And the other limiting equilibrium case when the ring is about to move downwards, that gives you the least possible value. So the takeaway from this is what you've got to do. Whenever you have to find greatest least values of any forces, when you have a rough surface, having friction, you consider limiting equilibrium case. Either it's going to move on one side or on the other side. Does that make sense? We've done questions like this. Now, I can't find that particular question right now, but the method for that is exactly the same. Yes, sir.
सर सर क्वेश्चन इसका है 2023 मई जून के पेपर में आया 42 वेरिएंट एंड सर मेरा इसमें ये क्वेश्चन है कि
सॉरी मुझे एग्जैक्टली बताओ कौन सा वेरिएंट है? मई जून 2022?
हाँ जी
ओके, जून 2022 पेपर 4 वेरिएंट
42
okay, yes. What question number?
I guess it's question number 3 or 4.
No, ये नहीं है. जो मैंने वीडियो पोस्ट किया ना, forces in equilibrium difficult questions वाली, that contains such questions. That contains from the recent papers from 2020 onward. I think there were like 3-4 questions like that. I think I've included 2 or 3 of them in that video. So if you have a look at that, it's the same idea that I've used there, that you consider the limiting equilibrium case. Okay, when you have an inclined surface as well, in that case, the same thing happens. You consider the limiting equilibrium case once when the object is just about to move upwards or it's about to move downwards. You'll have to consider one of those 2 cases.
So it's question number 5. Sorry about this.
Question number 5? Okay. In this case, they already tell you it's limiting equilibrium. And you have to find
paper is summer 23.
Okay, summer 23. Okay. 4-2.
Yes, sir.
Okay, this we actually have done live as well. Okay, so it says find the least possible value of P. And you have this inclined surface, which is rough surface, right? The idea is exactly the same. You have this force P acting in this direction. Okay, you've got this force P acting in this direction. And this force is basically holding or keeping this particle in equilibrium. If this force P was no longer there, what would happen? Because of the weight of the particle, it would start sliding downwards, right? Because of this weight component that's acting in this direction, it would start sliding downwards. What's the minimum possible value of P that would keep it in this position in equilibrium? How do you find that? You consider the limiting equilibrium case. You consider the case that the ring, that the particle is just about to move down the plane. It's just about to slide down the plane. You consider that case. That's what we have considered here. So that's limiting equilibrium. Okay, limiting equilibrium with the particle just about to move down the plane. That means one, F equals mu r, and second, friction is going to act up the plane because the particle is just about to move down the plane, and then you just equate the opposite forces, and that is going to give you that value of P. That's 1.41 Newton. Make sense?
सर इसमें मैं इस तरह से सोचता हूँ कि अगर लेट्स सपोज हमें लीस्ट वैल्यू चाहिए तो जहाँ पे मोशन जिस मोशन में वो जा रहा होगा पार्टिकल वहां भी फ्रिक्शन एक्ट करेगी ताकि हमें उससे लीस्ट वैल्यू मिले एंड टू गेट द ग्रेटेस्ट वैल्यू हम उसके ऑपोजिट रखेंगे फ्रिक्शन
नहीं, लेकिन फोर्स तो उसी डायरेक्ट, अच्छा फ्रिक्शन की बात करो. Yes, you can think of it like that. Yes, okay. For this force to be greatest, friction would have to act opposite to it. For this force to be least, friction would have to act in this direction. In that case as well, again, you have to use the limiting equilibrium case. Okay.
सर इसका क्वेश्चन में 6 पार्ट सी आप एक बार एक्सप्लेन कर देंगे, उसकी समझ नहीं आई थी.
Okay, let's actually stick to this concept first. We'll come back to that question number 6 later on. So least and greatest value. One case for this is when you have a rough surface, inclined surface, and there is friction involved. Okay, now let me open that here. This is one case. Another case is when you have a particle hanging from a string. Okay, you must have seen questions like that in 2021 papers. When an object is hanging from a string, in that case, when you have to find greatest or least value of something, what you do is you put one of the tension values equal to 0. You put one of the tension values equal to 0 in that case. Now, let me show you a question like that. Again, I included that in that video, forces and equilibrium difficult questions video. Let me show that to you here. It should be, yeah, right here. So cases like these. This is November 2021, paper 4, variant 2, question number 6 from that. In the second part, you see what they're asking for. They're saying find the least value of x for which this block remains in equilibrium in the position shown. This is the equilibrium position. You can see that in the diagram. What's the least possible value of x for which it would remain in equilibrium like this? Okay. Now I've explained the logic for this in detail there, but what you need to remember now is you will, in cases like this, when you have an object hanging from a string like this and it's in equilibrium, and you have to find least value of a force or the greatest value of a force, all you have to do is put one of the two tensions equal to 0. Put one of the two tensions equal to 0. Now, think about it. There's only one of them that you can put equal to 0. One is T1 and the other is T2. If you put T1 equal to 0, there would be no force that can balance the weight of the object, right? Weight is acting downwards. The only force that's countering weight is this T1 tension. If you put T1 equal to 0, weight cannot be counted and the object would fall down. So which is the other tension that can become 0? That's T2. So in order to find the least value here, you put T2 equal to 0. Okay. Now the logical explanation of this, you can find that there in the yearly playlist that you have for this particular paper, and in that video as well. I'm not going to go into that detail. Now, since your exam is tomorrow, this is what you can remember for now. You have to put one of the tensions to be zero, equal to zero, okay? In cases like these. And you can figure out which one of them can be zero. For example, in this case, this is another case like that. You have this particle, this block hanging in equilibrium from a string like this. And you have to find in the second part the greatest value of f for which the block remains in equilibrium like this. What's the greatest value of f in this case? Again, how do you find that? You have to put one of the tensions equal to zero. One of the tensions has to be equal to zero. Okay? And then you think about which tension you can input equal to zero. Okay? T1 and T2. Now on the left side, we only have a component of T1 acting. On the right side, we have one force F and another force T2 cos 53.13. Now, if T1 was equal to zero, we would have no force acting on the left side. If there's no force acting on the left side, what is going to counter this force F? No force can counter that, right? Okay. Think about vertical forces. Vertically, we have T1 acting here and T2 acting here. We have components of T1 and T2 acting in the upwards direction. Downwards, we have weight. Now, if we put one of these two equal to zero, the other can take care of that. So vertically, we don't have a problem. Horizontally, if we get rid of T1 from there, we don't have anything to balance the forces on the right side. However, if we remove T2 from here, the rest of the forces, they can get balanced. Okay, so that's the thing, that's what you can remember for tomorrow. Again, that's not complete logic for this. For that, you can have a look at the complete solution. But just remember, when you have to find greatest or least value of a force in a case like this, what you have to do is put one of the two tensions equal to zero. And this is how you can figure that out. Make sense? And in this case, you would have to put T2 equal to zero. And that will give you the maximum value of the force F. Is that okay? So this is the summary of that discussion that we just had. This is what you have to do for finding greatest least forces. Okay. Now, let me have a look at the next thing that you're asking about. Okay, so this we've already discussed. Question number 5. Okay, now let's have a look at this question. Ibrahim, can you tell me which exact paper it's from? Which exact paper is this from? March 24 variant for question number 7. It's going to be there in one of the recent videos that I've posted. I think the kinematics momentum, one kinematics with momentum. You can find the solution for that in that particular video. Kinematics with momentum difficult questions. It's the most recent video, one of the most recent videos that I've posted just in the last few minutes. You can find the solution to that in that video, kinematics with momentum video. Okay. Ibrahim, October, November 2022, paper 4-3, question number 3. Okay, let me have a look at that quickly. M1, November, paper 4-3. November 2022. Okay. Yes, Abdullah, that's correct. When you have, so in kinematics, when do you have to break your journey into parts? Now, again, I'll go back to that in a moment. This question that you asked about, this is a quick one, so I'll just answer that right now. In kinematics, when you have to find distance traveled, from one point to the other, you have to break the journey at the points where v equals 0. So whenever you have to find distance traveled, you always put velocity equal to 0 to check if the direction of motion is changing at any point. If it is changing, you have to break your journey into parts at that particular point. Okay, so when you input limits, break those limits at that part. For instance, if you have an object that's moving from time equals 0 to time equals 20, and you put v equal to 0, and it turns out velocity is equal to 0 when t equals 12 and when t equals 16, you can't find distance traveled by inputting limits directly from 0 to 20. You would have to break the journey into parts. You would have to find distance traveled from 0 to 12 separately, and then from 12 to 16 separately, and from 16 to 20 separately. You'll find displacement from for each of those parts separately, make them positive first, and then add them up together. Okay? You can't find distance traveled directly. When you have to find displacement, that can be done directly. But if it's distance traveled, that cannot be calculated directly. You have to break the journey. This is one example of that. You can take a screenshot if you want and have a look at this in your own time later. So if you have to find distance traveled by this particle in the first 10 seconds of the motion, you first put v equal to 0 to check that v is 0 when time equals 3 or time equals 4. So you can't find distance traveled directly. You'll have to break the journey into 3 parts, 0 to 3, 3 to 4, and then 4 to 10. Find the distance, find the displacement from each of those parts separately, make them positive, and then add them up together for finding distance traveled. Okay? Yes, that's an important thing that you need to remember. Now let me go back to that question. Okay, question number 3 from this paper. Okay, so this is the one that you're asking about, right? Question number 3. Now, let me just copy this on the side. We could work on that. All right. So we have this ring of mass 4 kilograms that is threaded on a smooth, circular, rigid wire with center C. The wire is fixed in a vertical plane, and the ring is kept at rest. At rest means it's in equilibrium. Okay. Mass of the ring is 4 kilograms. It's a smooth, circular, rigid wire. Center is at C. The ring is kept at rest. That means it's in equilibrium. With the light string connected to A, the highest point of the circle, you can see that there is the highest point of the circle. The string makes an angle of 25 degrees to the vertical. You can see that in the diagram. Find the tension in the string and the magnitude of the normal reaction of the wire on the ring. Tension and normal reaction, these are two things that we're looking for. It's an equilibrium problem. However, the problem is they've made it slightly complicated by making it a circle instead. Now, how do we think about this? Let's think about all the forces acting on this ring. What forces do we have acting on this ring? Let's represent them here. Mass of the ring is 4 kilograms, so weight is going to be 40 Newton. Weight always acts vertically downwards, so this is the direction of the weight that's acting here. What else? We have tension. Where does tension act? Tension acts away from the ring. What was that point A? Yeah, string was connected to the point A here. That's a fixed point. So tension is going to act in this direction. That's another force that's acting. These are two forces that are acting. What else do we have? Now you see, ring is in contact with this wire. Okay, wire, you can think of the wire as a surface. The ring is in contact with that surface. Whenever you have an object in contact with the surface, what you have is a normal reaction. Okay, you have a normal reaction. Now, where does normal reaction act? What's the direction of normal reaction? Reaction always acts perpendicular to the surface. Reaction always acts perpendicular to the surface. Now, what's the surface here? It's a circle. Remember paper one, what's a normal to a curve? It's a line that is perpendicular to the surface of the curve at that point. So normal reaction, where is that going to act? It's going to act perpendicular to the circle at that point. Something like this, right? The direction is going to look something like this. This is going to be your normal reaction. This is the direction of the normal reaction. These are the forces acting on this ring that we've got. And now the question is, how do we resolve the forces, right? Because it's equilibrium, we have to equate the opposite forces. But how do we resolve these forces? Since we don't have them horizontal or vertical right now, how do we resolve the forces? We have this force T. There are going to be two components of the force T, one acting to the right like this, and one acting vertically upwards like this. These are going to be the two components. Now, can we find some angles for that? If this angle is 25 degrees, can we say anything about this angle here? This is alternate angle. This is also going to be 25 degrees, right? Because these are alternate angles. If this is 25 degrees, can we find this component now? This is T cos 25. And what about the other component? This is going to be T sine 25. These are the two components that we've got for the tension. Okay. Now, what else? We have this normal reaction. How do we resolve normal reaction? That's the question now. Now, let's think about this. If you make a tangent at this point, tangent is always parallel to the direction of a curve of a surface. And tangent is also perpendicular to the radius of a circle. If you have a tangent at a particular point on the circumference of a circle, radius is perpendicular to that. So if this is the radius, tangent is perpendicular to both the radius and the normal. What that means is, this is going to be a straight line. So this direction of the reaction, if you join that with the center of the circle, it's a straight line. So the direction of the normal reaction is actually the same as the direction of this radius. Now, can we find the angle for this reaction now to try to resolve it horizontally and vertically? How do we do that? If this angle is 25, can we say anything about this angle? This is radius. This is also radius. It's an isosceles triangle. So this length is also, this angle is also 25 degrees. Now, if this angle is 25 degrees, what about this remaining angle? 180 minus 50, that's 130. So this complete angle is 130. If this complete angle is 130, what about this angle? 130 minus 90. What does that give us? That gives us 40. So this angle is 40. And that is what we were looking for. Because if this angle is 40, that means the angle that the reaction is acting at is 40 degrees here. So what are going to be the two components of reaction? One component is going to act along adjacent to the angle, which is going to be R cos 40, and the other component is going to be perpendicular to that angle on the other side of the angle, that is going to be R sine 40. Okay, these are two components that we get. This was great. R sine of 40 degrees. And now we've resolved the forces. Weight is not supposed to be resolved because weight is just vertical. We have resolved the other forces. Now we just equate them. We've got these horizontal forces. T sine 25, that's acting to the right. R cos 40 is acting to the left. T cos 25 is acting upwards. 40 is acting downwards. R sin 40 is acting downwards as well. We make two equations from them. The force is acting towards the left side. They're supposed to be equal to the force is acting to the right. So that means R cos 40, that equals T sine 25. That is one equation that we get from this. And upwards forces are supposed to be equal to the forces acting to downwards. That means T cos 25, that equals 40 plus R sine 40. So you have these two equations, you solve them simultaneously, and you get the values of R and T. I suppose you can do it after this, right? Make sense? Yes, for finding distance traveled, you always put V equal to 0 to check if the direction is changing. Okay. For displacement, you don't have to do that. For displacement, you don't have to do that. For distance traveled, you always have to do it. Okay, no problems. Okay, any other questions? Any other problems now? Any other problems quickly? So do check out those videos. I'll actually post the links to those two videos, those three videos in the group right now as well. So I posted one for forces in equilibrium, difficult questions on that yesterday. And I've just uploaded the three other videos, one for kinematics, one for Newton's second law of motion, and one questions where you have kinematics along with momentum. So the difficult questions that you find in recent papers, they're mostly about kinematics involved with momentum. So have a look at that as well. Right, I'll do this afterwards. Trying to find them right now. The WhatsApp group. Okay. Yes, let me know. Any other problems? Any other problems? Okay, just a reminder about tomorrow's exam. Again, some things are the same as for any other exam. That you have to make sure that you sleep well for any math exam. It's extremely important. Otherwise, you can end up doing a lot of careless errors. So have good night sleep. Night sleep is important. Don't just stay up the whole night and then thinking that you have a PM exam, so you can stay up all night and then sleep after 6 a.m. or 7 a.m. or something. At least have a few hours of night sleep. Okay. 3-4 hours minimum, and then you can sleep. You can wake up for further and maybe sleep again after studying for a couple of hours. If you want to have some sleep right before the exam, you can do that. But make sure to have night sleep minimum 4 hours, and then you can have 3-4 hours of sleep at another time as well. And then the other most important thing, make sure that you do not get stuck at a particular question. It's extremely important for mechanics exam, because the recent papers, if you look at them, they are coming. The recent papers are basically very, very long. Sometimes some of these recent papers, they are not even possible to complete in the time that's given. So how can you still get a good grade? If you get a question that's extremely difficult, that's mostly happening in the questions 6 and 7 in the recent papers, mostly question 7. So they have been nice enough to put that question at the end in recent papers. But if you end up getting a question like that in the middle, don't end up spending too much time on that. So if it's a 4 or 5 mark part and you spend like 3-4 minutes on that thinking about it and you can't figure out a direction, make sure to move on to the rest of the questions. If you can do all the other questions correct, the questions that are relatively simpler, the questions that are medium difficulty level, you can still get a very good grade. Okay, because if you're finding a question that's difficult, most other people are going to find the question difficult as well, of course, as long as you've prepared well for it. What you cannot afford to do is that you end up starting that question and trying to finish that in the middle of the exam, and that ends up taking like 20-25 minutes of your time, and then you're not left with enough time for the potentially easier questions that are coming up later in the exam. That is what can cost you the grade. Even if you get that question right at the end, The problem is you can end up losing marks on some easier questions because you won't have enough time left for them. So please don't get stuck. Do not get stuck in the middle. If you've spent some time thinking about a question, you can't figure it out, just move on and complete the rest of the paper first and then come back to that. Okay. Mostly when you have something like this, the threshold takes care of that. Okay. So that's very important for mechanics papers, recent papers. I can tell you for sure, some of them impossible to complete in real time. There are not many like that. At least 2-3 papers in the last couple of years, they're not possible to complete in real time, especially when you have that exam environment. It will be possible. So relax. Do the questions that you are comfortable with first, and then try to get as many method marks on the remaining 1 or 2 questions that you can't figure out as completely. Leave them for the very end and try to get as many method marks as you can on those questions. Now, in mechanics, a lot of times what happens is you end up losing accuracy marks as well. Why? Because okay, I'm sorry, I got disconnected. So I was basically saying, when you have angles like this, sine or cos of something, when you're doing these calculations, use minimum 4 significant figures when you're working. If you round it off too early, you will end up losing accuracy marks at the end. Okay, so please do not do that. Please do not do that. If you write something in decimals in your working, first of all, make sure that you have 4 significant figures there. Okay, make sure that you have 4 significant figures there. Ideally, you should leave it in exact form like this until the end and then do that calculation at the very end. But some people find that a bit complicated. So if you do write down the values, write them to minimum 4 significant figures. Okay, otherwise people end up losing a lot of accuracy marks in mechanics, basically. Okay, so that is important for you to remember. And also make sure that you show all working, just like for paper 1. If you have a quadratic equation or a simultaneous equation, show working for that. Okay, make sure that you show working for that. If you have to input limits somewhere, show how you're inputting those limits, and then write down the answers. Don't write down the answers directly without showing sufficient working for that. Okay, so these things are really important to remember, especially the point that you do not get stuck at a question, because otherwise you would be losing out on some of the potentially easier questions. Okay, all right. Now let me have a look at another one. So now you're asking about this question. In the power formula, can we use work done against resistance? Well, for what exactly, Rukaya? If you're asking, if you have to find power generated by some object, we'll have to use this formula, driving force into velocity. The force that you use there, or are you asking about the other formula? Work done over time. We generally use work done by the driving force here, right? Because power is generated by the force that is the driving force generally. Where exactly you're talking about resistance, you'll have to give me an example of that. Okay. Okay. Now let me have a look at this question. June 23, paper 4-2, question number 6, part C. June 23. 4-2, question 6, part C. Okay, so what about this? Now I'll have to do the first two parts quickly as well to understand what's happening in the next part. Okay, so this is June 23, paper 4, variant 2. Question number 6 of that. It says, a particle P starts at rest, so it starts at rest, and moves in a straight line from a point O. At time t seconds after leaving O, the velocity of P, v meters per second, is given by this. Okay, so this is the velocity function. P has velocity 8 meters per second when time equals 4 and has velocity 13.5 meters per second when time equals 9. Show that B equals 3 and C equals minus 0.5. Okay, so how do you do this? You've got this velocity function, V equals BT plus CT raised to the power 3/2. And they've given you these two pieces of information. You just input those values here. Why is this just one mark? Let me think about it. If you just input those values of t, let me just see what we get from that. If you input t equals 4, you get 4b plus 4 raised to the power 3/2 times c equals v, which is 8. So I'm inputting this first piece of information here, and that's giving me an equation in terms of b and c. Okay, so what you can actually do is, yes, so this will work. So you won't have to solve this. You can actually make this process slightly quicker like this. Okay, so this is the velocity function. What I'm doing is I'm inputting t equals 4 and v equals 8 in this. What does that give me? That gives me 8 equals 4b plus 4 raised to the power 3/2 times c. And then what you can do is you can just input these values of b and c in this. Input b equals 3 and c equals minus 0.5. It would satisfy the equation. And that means this is a possible value. And then you do the same thing with the other velocity and time as well. In fact, you can make it even shorter. I'm sorry. So you can make it even shorter than this. Since you have to show this, you don't have to calculate this again. Just input those values. Input v equals 3t minus 0.5 t raised to power 3/2. That will be even quicker. Since you just have to show that v equals this and c equals this, you don't have to find those values. Just use them. You say v equals 3t minus 0.5 t raised to power 3/2. And now let's just check if these two values that are given, they satisfy this equation or not. So one value is t equals 4 and v equals 8. Input this here and see if the equation is satisfied. And then again, you input t equals 9 and v equals 13.5 and see if this pair also satisfies this equation. Let's do that. We get 8 equals 3 into 4 minus 0.5 into 4 raised to the power 3/2. And that's going to give you 8 equals 8. That's it. And then similarly here, you say 13.5 equals 3 times 9 minus 0.5 into 9 raised to the power 3/2. And you say 13.5 here on the right side. If you calculate this, this should turn out to be 13.5 as well. And that verifies that these values are true. Okay, so that will be the quickest way of doing this. Okay. Now it says, find the acceleration of P when time equals 1. How do you find acceleration? You've got the velocity function now. The velocity function is 3t minus 0.5 t raised to the power 3 over 2. That's the velocity function. How do you find acceleration from velocity? You differentiate it, right? You differentiate it. We get a equals 3 minus 0.5 into 3 over 2 t raised to the power of 1 over 2. That's the acceleration that we get. Okay. Well, the paper says 3 significant figures, but that's for the final answer. The paper says 3 significant figures for the final answer. For working, you need minimum 4 significant figures. Otherwise, you don't get correct answers. Okay. You can't round off in the middle. All right. So this is what you have. Now you put t equals 1. Let's input t equals 1 here. What do we get from this? A equals 3 minus 0.5 into 3 over 2 times 1 raised to the power 1 over 2. Can somebody tell me what this value is? I don't have my calculator with me right now. What's this acceleration value? Quickly, Abdullah, you were the one who asked this. What do we get from this?
So just give me a second.
2.25, right? This will be 0.75 and that should give you 2.25. Right? Okay. Now part C says, find the positive value of t when p is at instantaneous rest and find the distance of p from O at this instant. Now we've got the velocity function. The velocity function is 3t minus 0.5 t raised to the power 3 over 2. That's the velocity function. 3t minus 0.5 raised to the power t raised to the power 3 over 2. Good. Now find the positive value of t when p is at instantaneous rest. What does that mean? You put v equal to 0. What do you get from that? V equals 3t minus 0.5 t raised to the power 3 over 2. Find the value of t from this. How do you do that? You can take t common. If you take t common from this, that leaves you with 3 minus 0.5 t raised to the power 1 over 2. That means either t equals 0 or 3 minus 0.5 t raised to the power 1 over 2 equals 0. 0.5 t raised to the power 1 over 2 equals 3, t raised to the power 1 over 2 equals 6, and t equals 36. They asked you for the positive value of t. The positive value of t is 36. Now that's one thing that you were looking for in this part. Now it says find the distance of p from O at this instant. Now understanding the statement is extremely important. Distance of p from O. What does that mean? If we have a particle traveling like this, it goes from A to point B and then from B to point C. If you're asked about distance traveled, that is 170 meters. 100 meters here and 70 meters here. That's 170 meters. Distance traveled is 170 meters. If you're asking for displacement, that will be this 30 meters. That also makes sense. So distance traveled and displacement, they are easy to understand. But sometimes they say something like this: distance AC. Now, distance AC does not mean that the distance the particle travels from A to point C. It means distance between the points A and C. Distance between the point from the point A to the point C. That's the same as displacement, right? The word is distance. The word used is distance here, but what it actually means is displacement. Okay, so distance AC means displacement in this case. When you have to find distance traveled, they would say distance traveled or distance covered or something like that. Okay. Now, if you go back here, in this case, they're saying find the distance of P. P is that particle from O, from the starting point. Distance of P from the starting point. What does that mean? That's the displacement at this point. Displacement of the particle from the point O at this instant. Okay. So we are actually asked about displacement here. How do you find displacement? For displacement, you don't have to check for change in direction or even worry about that. So all you have to do is just integrate it and input limits from 0 to 36. That's all that you have to do. That's pretty straightforward, actually, isn't it? You've got the velocity function, you integrate it, it becomes 3t squared over 2 minus 0.5 t raised to the power 5 over 2 divided by 5 over 2, and you just input the limits from 0 to 36. And that should give you the result. Okay. Why would you do t equals 4 and t equals 9? That's even for distance traveled, you would not do that because velocity is 0 only at t equals 36. The particle is not even changing direction until 36. So in this case, distance traveled would also be the same. You won't have to break the journey in this case because velocity only becomes 0 in this case when time is 36. So between 0 and 36, there is no change in direction. So in this case, distance traveled and displacement, they mean the same thing because the direction is not changing. Okay. So you don't have to worry about changing, breaking the journey in this case anyway. Okay. So I hope that makes sense. You can do that. All right. Any other problems? Any other problems with me? रेड बुल पी के फिर एकदम आप इकट्ठा ही क्रैश करेंगे, वो पेपर में ना क्रैश हो जाए फिर. I won't suggest taking that risk, and I'm not sure if your brain is going to work fully with that as well. Okay. All right. So if there are no further questions on this, let me just explain that question very quickly then. The one that we talked about earlier, and that because that's an important question that keeps coming up again in recent papers as well. Let me see if I can find that quickly. It was forces. Yeah, let's try this one for instance. Okay, let's understand this question quickly with proper logic as well. I'll come back to you in a moment. I'll do this quickly. The second part of this only, not the first part. Well, I did not even copy the second part. First part is pretty straightforward. Okay, let's have a look at this question quickly. Now the second part has less marks because that uses some of the working that you've done in paper 1 as well, and in part 1 as well. But in this case, the working is going to be longer because we're doing second part directly. So keep that in mind. That some of this working you would have already done in part A, but I'm doing that again here. Okay, let's read the question statement. So it says the diagram shows a block of mass 10 kilograms suspended below a horizontal ceiling by two strings AC and BC of lengths 0.8 meters and 0.6 meters. Attached to fixed points on the ceiling, you can see that here. Angles are given. In fact, this is 90 degrees. You have to find the other angles using those lengths. The block is in equilibrium, and there's a horizontal force F Newton acting on the block. All of that is given on the diagram. You can see that. The only thing that's not shown there is that the block is in equilibrium. Now, in the second part, it says find the least value of x for which the block remains in equilibrium in the position shown. Now, how do you find that? How do you find the least value of x? Okay, I'm sorry. I think I copied that from another question, the second part. What was this? There's no x there. It was supposed to be f. Okay, let's look at the second part here. It says Find the greatest value of f for which the block remains in equilibrium in the position shown. Okay. Now this is F Newton. We need to find the greatest possible value of f. Now, how do you do that? First of all, you resolve the forces. How do you resolve the forces? For that, you need the angles. How do you find these angles? You're given the two lengths, 0.8 and 0.6. If these are 0.8 and 0.6, can you find the third length? 0.8 squared plus 0.6 squared, square root of that, that will be the length AB, because it's a right angle triangle. AB is the hypotenuse of that. What does AB turn out to be? AB equals 1. So this length is 1 meter. Okay, this length is 1 meter. Now, if this length is 1 meter, let's call this angle something. Let's call this angle alpha. Let's call this angle beta. Can we find sine alpha? Sine of alpha, that will be perpendicular over hypotenuse. What does that become? 0.6. Cos alpha, adjacent over hypotenuse, that's 0.8. Similarly, for beta, sine is 0.8 over 0.1. Perpendicular over hypotenuse, that will be 0.1. And cos beta will be 0.6 over 1, that is 0.6. So we've got alpha and beta. Okay, we've got their sine and cos. That's all that we need, right? In our working, we need sine and cos. So we don't have to find the angle necessarily. We can just use these lengths now. Use these values of sine and cos. Now that's all that these lengths are used for. We can get rid of them now. Let's resolve the forces. What are the forces acting on this block? You've got weight acting in the downward direction. Weight acting downwards, that's 100 Newton. Two tensions, one acting on the left side, let's call this T1. And one acting on the right side, let's call this T2. These are two tensions that are acting. And we've got this force F. Let's resolve those two tensions quickly. One acting to the right. If this angle is beta, this is also beta. So this is T2 cos beta. And the vertical component is going to be T2 sine beta. And similarly for T1, the components are going to be one component on the left side. If this angle is alpha, this is also alpha. So it becomes T1 cos alpha. And the vertical component becomes T1 sine alpha. These are the components that we have for these forces. Now, let's just equate the opposite forces. We've got some forces acting to the right. These are the forces acting to the right. T2 cos beta and F. We've got one force acting to the left, T1 cos alpha. Upwards, we've got T1 sine alpha and T2 sine beta. Downwards, we have 100. Since it's an equilibrium, the opposite forces are supposed to be equal. Forces acting to the left, they're equal to forces acting to the right. And the forces acting upwards are equal to the forces acting downwards. Just equate the opposite forces. What do you get from that? You get T1 cos alpha. That equals F plus T2 cos of beta. And then upwards forces and downward forces, they're supposed to be equal. So that means T1 sine alpha plus T2 sine beta. That should equal 100. You get these two equations? Now let's input values in them. What's cos alpha? Cos alpha is 0.8. So it's 0.8 T1. That equals F plus cos beta is 0.6. So that's 0.6 T2. And then sine alpha is 0.6. So this becomes 0.6 T1 plus sine beta is 0.8. 0.8 T2 equals 100. Now, how do you think about this? One way to think about this is that you consider, one way to think about this is that you have to find greatest value of force, right? You consider these two equations. And think about mathematically, how can you maximize the force F? How can you maximize F, right? That's what you think about. Let's make F the subject here. If we make F the subject, that means 0.8 T1 minus 0.62. And this is the other equation that we've got. Now, f needs to be maximum. F needs to be maximum. Now, think about it. F equals 0.81 and minus 0.62. How can we maximize the value of f? For f to be maximum, T1 needs to be maximum and T2 needs to be minimum, right? The positive value has to be as big as possible and the negative value has to be as small as possible. So we want T1 to be as large as possible and T2 to be as small as possible. Now, how large can T1 be? Well, we can't put a value to that as such. However, we can't make that extremely big. Why? Because we know that this sum is also equal to 100, is also equal to 100. So if T1 is too big, for example, if T1 is maybe 500, then 0.6 into 500, this would already be 300. You can't have the sum equal to 100 then. So you can't maximize T1 arbitrarily. You can't make it extremely large. Okay. How large can we make it? It's not very clear. Okay. However, if we think of T2 instead, how small can we make T2? What's the smallest possible value that T2 could have? We can't make it negative. The smallest possibility is that we make this 0. So for f to be maximum, what we do is we say T2 should be equal to 0. Tension in the second string, the one on the right side, that should be equal to 0. For f to be maximized, what does that give you? You get 0.8 T1 minus 0.6 times 0 here. From the other equation now, since you put T2 equal to 0, what you can do is you can find the value of T1, the corresponding value for T1, that gives you 0.61 plus 0.8 into 0 equals 100. And that gives you T1 equal to 100 over 0.6. What's that? 0.6 is 3 over 5. That will be 5 over 3, 500 over 3. 166.67, right? That's what T1 turns out to be. Put that in the first equation. That gives you F equals 0.8 into 166.67. That's 4 over 5 of this value. What does this turn out to be? 5 with 33, and then, yeah, 133.33 Newton. That's the greatest possible value of F that you can get here. So you see, what you did was you just put one of the tensions equal to 0. So that's what I told you earlier, that you put one of the tensions 0 in cases like these. Okay, and then you can think of this on from the diagram as well. Which tension can be put equal to 0? T1 can't be 0 here, because if T1 was 0, we won't have anything to balance these forces on the right side. Okay, so T1 is the only force acting on the left. If we can't make that 0. T2, however, can be made 0, because if T2 is 0, T1 can handle the weight. It can take care of the weight. And on the right side, you already have F as well. So on the right side, F takes care of it. Okay. All right. So that's how you deal with problems like these, where you have to find the greatest possible value of a tension or least possible value of a tension of a force. In cases like this, where you have tensions involved, you put one of the tensions equal to 0. Okay. Now let's have a look at the next one. March 21, question number 7. Okay. And then I'll come to that. November 2018, paper 4-2. All right. March 21, right? Okay. Question number 7, part B. Abdullah, we looked at this the other day. When did we do this paper? March 21. On 24th of April. We did this on 24th of April. We did this the other day. You were not there? Is there a specific question here? Any specific problem that you have from this? The second part was here was quite complicated, yes. Any specific question that you have from this? Part B, yeah, but where exactly? So what we've done is we have used, so let me just read the question statement again. It's given that the plane on which Q rests is rough. Okay, so this plane is rough. And after they move 1 meter, their speed is 0.6 meters per second. The work against friction in this part of the motion is 0.5 joules. All right. So what we have done is we have used the work energy principle. Work done by driving force equals change in kinetic energy plus the change in potential energy plus work done against resistance. Now the problem is both the particles are moving in different directions and their angles are also different here. You cannot, or you should not, consider this as a single system. Find each of the relevant quantities for the two particles separately. Find their work done by driving force separately, find their kinetic change in kinetic energy separately, find their change in potential energy separately, because their heights are changing differently, their masses are their heights are changing differently, their masses are different, their speeds are different. So what we do is we apply this equation on each particle separately, as in separately in the sense work done by driving force for P and Q, both of them are considered separately here. So P was moving up the plane, Let me check here. Okay, P is moving down the plane. It says P is moving down the plane. P is moving down the plane. If P is moving down the plane and it has traveled 1 meter, work done by driving force will be 0.8 into 0.1, 0.8 into 1 for P, and then T into 1 for Q, because the driving force for Q is this force T. So that's T times 1. And then change in kinetic energy. We are given that their speed is 0.6, the final speed. So we're using that here as the final speed for both of them. Initial speed for both of them was 0 because they're connected. And then their masses. So change in kinetic energy is pretty straightforward. What about the change in potential energy? Now that is the complicated part here. So what you have to do is you have to figure out the change, the vertical change in height, right? Using simple trigonometry. So for example, if particle P moves down by 1 meter, you think of this right angle triangle. Is there? That by using trigonometry, and that gives you the change in height, that's 1/2. And this is decreasing, so we use minus 1/2 here for that reason. Similarly, on the right side, Q is also moving upwards by 1 meter. You use this right angle triangle to figure out the change in height for Q. 1 meter is the hypotenuse, 45 degrees is the angle. You can find the height using sine again. So HQ turns out to be under root 2/2. This is going to be positive. Why? Because the height is increasing for Q. That's positive here. And then you have work done against resistance. For P, T is part of the resistance. So we use T into 1 here. And work done against resistance for the other particle was given. Work done against friction, that was 0.5. We use that here as well. We got this equation and then solved that to find the value of M from that. I will be posting this again as well today in the difficult questions on work, energy, and power, the complete explanation for this. But you already have that recording available for this paper. You can have a quick look at that. and it will make sense to you if you want more details on this. All right. Yes, Rukaya. Weight is considered as forward force or a backward force. Okay, weight is part of forward force and backward forces, but it's not part of driving force or resistance. Okay, it's not part of driving force or resistance. Yes, Abdullah?
सर इसमें वर्क डन बाय ड्राइविंग फोर्स मेरे पास इसकी समझ नहीं आई थी, बाकी रिलेटिवली हो गए थे इस बात। एंड सर एक और सवाल कि इसमें हमने दो पार्टिकल को इस वजह से कंसिडर किया क्योंकि एंगल्स डिफरेंट थे, तो डिफरेंट सिचुएशन इस वजह से हमने कंसिडर किया ना।
बिल्कुल, इसको अगर आप इकट्ठे लोगे इट विल बी एक्सट्रीमली कंफ्यूजिंग। काइनेटिक एनर्जी में इकट्ठे कर सकते हो यहाँ पे, बिकॉज इसमें स्पीड्स उनकी इकट्ठे चेंज हो रही हैं, बट यू कांट डू द पोटेंशियल एनर्जी चेंज टुगेदर। यू हैव टू कंसिडर देम सेपरेटली। ओके,
यस सर।
उनको आपको अलग देखना पड़ता है। ऑल राइट, okay, let's have a look at one more question. Paper for one. Okay, I'm sorry, I got disconnected again. Can you guys see my screen again?
यस सर।
Okay. It's taking time to load.
सर
Yes.
सर जब हम स्केचिंग करते हैं क्वाड्रेटिक क्वाड्रेटिक ग्राफ की इन हेवन ऑफ कोर्स, उसमें सर टर्निंग पॉइंट उसका कैसे लेते हैं? मतलब जैसे हम P1 में लेते थे, लाइक उनको जो फॉर्म दी होती है कंप्लीटिंग स्क्वायर,
Minus B over 2A.
-B/2।
But the quickest way of doing this is आपको ना M1 में you don't have to show that working for finding the turning point, etc. इसका ना आसान तरीका क्या होता है क्वाड्रेटिक में, just put that function on your calculator and that makes things much simpler. आप उसको ना कैलकुलेटर में, फॉर एग्जांपल अगर आपको उसकी फंक्शन है, अच्छा ये टाइम दे रहा है इसको लोड होने में, आई जस्ट शो दैट टू यू क्विकली इन द मीन टाइम। आपने बस जाने इक्वेशन सॉल्विंग फंक्शन में पोलिनोमियल डिग्री 2, अगर आपके पास कोई फंक्शन है मे बी x² + 7x + 12, आप क्या करो, x² से कोएफिशिएंट 1 हो गया and then you have 7x and then you have 12. It gives you the x-intercepts. This is the first x-intercept, -3. This is the second x-intercept, -4. And then you can press the equal button again. You get the turning point's x coordinate. That's -7/2. You press the equal to button again, you get the y coordinate of the turning point, that's -1/4. तो आपको quadratic functions के turning points directly calculators में मिल जाते हैं.
ओके ओके
Okay, उस equation solving वाले function को use करते हैं.
Sir, is that particular calculator allowed in Pakistan?
Yes, it's definitely allowed. It is allowed.
We are not allowed to use that calculator.
Who's this?
Sir, that's Jarif. It's me.
Who said you're not allowed to use it?
Sir, our school doesn't allow us to use that calculator. They say that it's much advanced. We use the 911 ES plus.
maybe they are talking
911.
about graphical.
No, not
No,
the
this
graphic.
was not.
The one,
This was ClassWiz.
the ClassWiz, it's not allowed. The ClassWiz is not allowed for us.
No, but that's just a restriction that your school might have put for you, but Cambridge allows it. So if you go to a center, they must allow it because it's supposed to be standardized across the countries wherever Cambridge exams are taken. It should be the same policy for everyone. So it's not about this being allowed in Pakistan but not being allowed in Bangladesh or UAE. That cannot be the case. Cambridge does allow it.
All right, sir.
Yeah. So maybe you can try discussing this with them.
We did.
Because with the school admin or with the
Yeah, we did.
invigilators?
School admin, they're like, it's not allowed by us, so it's not allowed.
Sorry?
They said it's not allowed, then it's not allowed from our school itself. So we are not allowed to use it. Few students took
Okay.
it to exam. They confiscated the calculator during the exam last year.
So the Cambridge exams or the school exams?
The board exam, sir, the A levels AS exam, the one that I did last year.
Is your center the same as your school? Your center is at your own school?
Yeah.
Oh, okay. All right. That so we don't have the center the students here, they don't have their centers at their own schools. Generally, it's administered by Cambridge at some other places. But okay, all right. Okay, November 2022, paper 4, variant 1. It's not opening here. I'll just open it somewhere else here. Paper. Okay, I'm sorry about that. Okay, this one. Question number 6 from November 22, paper 4, variant 1. Okay, let's have a look at this quickly. Looks like a good one. And it's in work, energy, power as well. The second part of this is least. Let's try this one. Okay, I think the first part is not that difficult, right? The first part of this. Is that correct? Okay, but what I'll do is I'll do both parts quickly, and I'll need some help with calculations. I'll just bring my calculator quickly. Just give me a second. I will bring my calculator. So we can speed up the calculations quickly. Where's that? Okay, let's try this one. So this is from November 2022, paper 4. And what was it? Paper 4, variant 3, variant 1. November 2022, paper 4, variant 1. Let's write that here. Okay, let's try this. It says the figure shows particles A and B of masses 4 kilograms and 3 kilograms respectively. And they're attached to the end of a light insensible string that crosses over a smooth pulley. The pulley is fixed at the top of the plane, and the angle is 30 degrees. The A hangs freely below the pulley and B is on the inclined plane. String is taut, and the section of string is being started. Okay, so all of this, you can see that in the diagram as well. I'm just going to highlight this, the masses, because then I can just get rid of this from here. Okay, so this is what the situation looks like. In the first part, it says it's given that the plane is rough and that the particles aren't limiting equilibrium. Limiting equilibrium means friction is at its maximum value, F equals mu r. Find the coefficient of friction between B and the plane. We have to find the value of mu. Now, how do you do that? How do you find the value of mu here? Let's think about it. Let's think about all the forces acting on these two particles. At A, we've got weight of the particle acting. What's the weight of A? That's 40 Newton. There's going to be tension acting upwards. Weight of B, that is 30 Newton. And tension is going to be acting in this direction. What other forces are acting? At B, we also have reaction that acts in this direction. Since they're talking about limiting equilibrium, that means there's friction as well. Where does friction act? We would actually have to think about that. Are the particles about to move up the plane or down the plane? We are not given that. So we'll have to figure that out. Which direction are the particles just about to move in? It's not clear from here. They don't give us that information. However, you can actually think of it directly like this. This is 40 Newton and this is 30 Newton. And all of this 40 Newton is acting vertically downwards. And only a part of 30 Newton is going to act in this direction. So the force acting towards the left is obviously greater. Okay. The force acting towards the left side, or on A downwards and on B to the left side, that is greater. That means the particle B is supposed to be just about to move up the plane. All right, that's what is about to happen. Now, where does friction act? Friction opposes that. So friction is going to oppose that and act in this direction, down the plane. Friction acts in this direction. These are all the forces that we've got acting on the two objects. Okay, now let's resolve them. We only have to resolve the weight here. That's 30 Newton. There are two components of weight. One component is going to act here. If this angle is 30, we know that this angle here is also 30 degrees. This is 30 cos 30, the component that is adjacent to the angle. And the component on the other side of the angle, that will be 30 sine 30. These are all the forces that we've got. Now we just have to equate these opposite forces, right? Now let's talk about A first of all. T is supposed to be 40. So by equating the opposite forces acting on A, we can say the value of tension is supposed to be equal to 40 Newton. All right, T is supposed to be 40 Newton. Now, what else? Forces acting on B. We've got some forces acting along the plane. That's tension, friction, and 30 sine 30. They're supposed to be equal. Some forces acting perpendicular to the plane. So according to the plane, you can see left, right, up, down. They're supposed to be equal. So this was for A. What about B? For B, we can say the forces acting to the left side, that's P, that should equal the forces acting to the right. They are F and 30 sine 30. And upwards force, that's R, that should be equal to the downward force, that's 30 cos 30. Okay. Now we just solve these three equations. We know that tension is 40. We can put that here. We can say 40 equals F. Since it's limiting equilibrium, friction is supposed to be at its maximum value, which is mu R. So we say this is mu R plus 30 into sine of 30. Sine 30 is 1 over 2. So we can say that's 30 into 1 over 2. R equals 30 into cos of 30. What's that? That is under root 3 over 2. All right. Now we put that value of R here as well. What does that give us? 40 equals mu into 30 under root 3 over 2 plus 15. And you can see what the value of mu turns out to be from here. Can somebody do this calculation for me quickly? What do we get? 25 divided by 15 and by under root 3. And that's giving me 0.96225. 0.962. If you want to write the answer to three significant figures, that will be 0.962, and that's your final answer. Okay, that's the first part. Pretty straightforward, easy 6 marks, right? That was the first part. Now let's look at the second one. Okay, what about the second part now? It says it's given instead that the plane is smooth and the particles are released from rest. Okay. It says it's given instead. Instead means whatever we did in the first part, that's no longer relevant. Okay. In the first part, the plane was rough. Now it's smooth. So there's no friction acting anymore. The particles are released from rest when the difference in the vertical height of the particle is 1 meter. So this difference between vertical heights is 1 meter. Use an energy method to find the speed of the particles at the instant when the particles are at the same horizontal level. Now, how do we think about this? Energy method, what does that mean? Work energy principle, that's work done by driving force, that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. That is what we've got to use here. Okay. Now, how do we use that? Let's think about it. What information do we have? If the particles are released from rest, so the starting speed, the starting velocity is 0. We need that for kinetic energy. Keep that in mind. The difference between vertical heights is 1 meter. Okay, so we'll keep that in mind as well for a change in potential energy. But we need to figure out how much has A moved and how much has B moved. We'll think about that in a moment. It says use an energy method to find the speed of the particles at this instant. Okay, so how do we think about this? Now, for using this method, we need the driving force and the resistance. So we need to represent the forces acting on these particles. What are the forces acting on these particles again? We have the weight of the objects. For A, we've got weight acting downwards, that is 40 Newton. But remember, weight is not considered a driving force. Keep that in mind. Weight is not going to be considered a driving force. Okay? Upwards, we've got tension. Now, we don't know what the value of tension is. Okay? You cannot use the value of tension from the first part. That was the case when the objects were in equilibrium. They are not in equilibrium. Okay? They're not in equilibrium. So tension value is not 40 anymore. Okay. Now, what about the forces acting on B? There is reaction. Again, we do not, in this case, we don't need that as such. right? Because that's normally used for cases when you have friction. In this case, there's no friction that's involved. What about the other forces? There's weight acting downwards. Again, that's not relevant here as such. Why? Because this is 30, right? Yeah, weight is going to be 30. It's not relevant for these calculations because that's not going to be part of driving force or resistance. What else? We've got tension. Tension acts in this direction. That is going to be important. Tension is one force that's acting. Okay. Now what happens is when the particles start moving, A starts moving downwards and B starts moving up the plane, right? These are the directions in which these two particles move in. Let's input values in this formula. Work done by the driving force. Let's do that for the two particles separately. What's the work done by the driving force for particle A? The problem is, although in this case, in fact, there's no driving force for it. So in this case, for A, it will be 0. What about B? Driving force is T, but the problem is we do not know how much has B moved in this direction. So that's the key thing that we need to figure out in this question. How much has B moved up the plane and how much has A moved down the plane? If you can figure that out, the rest of it is not going to be that difficult. So the main problem here is figuring out how much does A move downward and how much does B move up the plane. Now let's think about that. Let's think about how we can figure that out. Let's make a triangle here on the side, which maybe looks something like this. Now it will require some thinking. So we'll think about this in a moment. This is supposed to be 1 meter. Now let's suppose A was here, A is supposed to move downwards. And B is, let's suppose here, B is supposed to move up the plane. Now A is moving downwards and B is moving upwards. What has to happen is, whatever distance A travels downwards and whatever distance B travels vertically upwards, their sum has to equal 1 meter, right? So basically, let's say when A comes downwards, when they come at the same level, let's say A is here, and maybe B is here. Now think about it. This total length was what? This total length was 1 meter. The total length is 1 meter. Now, if the total length is 1 meter, A has traveled some distance from the top to this point. Let's call that HA, let's say. The change in height for the object A. Now, whatever distance A has traveled downwards, since A and B are connected, B would have traveled the same distance along the plane. The same distance along the plane, B would have traveled here. So this is going to be HA. Does that make sense? Let me explain it using numbers. Let's say A moves downwards by 0.4 meters or maybe 0.6 meters. Now, we don't know how much that distance is exactly, but let's say it was 0.6 meters. Then if A moves 0.6 meters downwards, B would also move 0.6 meters up the plane like this, right? That will be the same distance. So we say, let's say this is HA. Okay. So these two will be the same. Now, what about the change in height for B? What would that be? What's the change in height for B? This is going to be the change in height for B. HB. Vertical height change for B, that is this. Can we somehow connect HA and HB here? It's a right angle triangle. Let me make this slightly smaller. This right thing, this is 30 degrees. So we have this right angle triangle in which this is HA and this is HB. HB is perpendicular, HA is hypotenuse here. What's the ratio between perpendicular and hypotenuse? It's sine. So we can say HB over HA is supposed to be equal to sine of 30. And also, we know the sum of HA and HB, what should that be? Since its total distance was 1 meter, the difference between their perpendicular heights, HA plus HB, that should also equal 1 meter. The sum of these heights, these vertical heights, that also has to be equal to 1. All right. Now we can use this to find the change in height for A and the change in height for B. Let's see what this turns out to be. HB equals sine 30 is 1 over 2, so it becomes 1 over 2 times HA. We can put that here, and we get HA plus 1 over 2, or we can say that's 0.5 times HA equals 1. What's the value of HA that we get from this? 1 over 1.5, which is going to be 0.67, right? Let's use this as a fraction. 1 divided by 1.5, that will be 2 over 3, right? HA is 2 over 3. Now, if HA is 2 over 3, what about HB? HB will be half of that. That's 1 over 3. Okay, I'm sorry about it. मेरी बेटी ने जाके इंटरनेट की तार उतार दी थी, LAN cable, and I had to get reconnected, and you're back now. Can you guys hear me again and also see my screen again? Okay, I'm sorry. The other account got disconnected as well. You can just change that name. But Okay, I'm sorry about that. So this is where we were. We found out the height for A. The height for A turned out to be 2/3, and the height for B, the change in height for B turned out to be 1/3. So we found the change in height for both of them. Okay. Now, once we have the change in height for both of them, the rest of it is relatively straightforward now. Work done by driving force, that equals change in kinetic energy plus the change in potential energy plus work done against resistance. Now, what's the work done by driving force for A? There is no driving force for A. Okay. There's no driving force for A. So that's 0. What about the driving force for B? It's going to be tension into the distance traveled in this direction. What's the distance traveled by B in this direction? So let's say B comes here at some point here and A comes to this point here. Now we know that this distance that A travels downwards, that is how much? 2/3 or 0.67, 0.6667. So this is also 2/3. And what about the change in vertical height for B? We know that that is 1/3. This is what we know. All right. Now, what's the driving force for B? Tension. Tension multiplied by 2/3. Okay. Then on the other side, kinetic energy. Change in kinetic energy. Let's talk about A first of all. A starts from rest. And we have to find the speed of the particles when they are at the same horizontal level. So we can say the final speed at this point is V for A and also V for B. They're supposed to be the same because they're connected to each other. Half into M. What's the mass of A? Mass of A was 4 kilograms, right? Into V squared minus 0 squared. Now, for kinetic energy, we could consider them together as well by taking 7 here. But let's just do this that separately here. And then you have 1/2 into 3 into V squared minus 0 squared for B. These are the change in kinetic energies for the particles A and particle B. Okay. Now, what about the change in potential energy? A is moving downwards. A has moved down by 2/3 units. Okay, 0.667 units. Change in height. Mass is 4 into A, which is 10, into height, into G, that's 10. Height, the change in height is negative, so we have to put negative here, so it becomes minus 2/3. That's the change in potential energy for particle A. I'm writing A values here and B values here. Plus change in potential energy for particle B. How much is the height of B increasing? It's increasing by 1/3 units. Mass was 3 into 10 into height, that is 1/3. These are the changes in potential energies. Plus work done against resistance. Okay, I'm sorry. There was a plus here. Plus work done against resistance. What's the work done against resistance now? A is moving down the plane. This tension is acting as resistance for A, right? So we would say that's T into 2/3 plus work done against resistance for B. There's no resistance for B. There's only weight component that's opposing B. And we don't consider weight as either driving force or tension. So we're not going to consider that. Okay, so that's a 0. Now, in such problems, tension generally gets cancelled out. So in this case, it gets cancelled out as well. This term and this term, they get cancelled out, and you can solve the rest of it to find the value of V and see what that turns out to be. 0 equals 2V squared plus 1.5 V squared minus, evaluate this, 40 minus 40 into 2 divided by 3 plus 30/3. That's giving me minus 50/3. So this should be 50 over 3 equal to 3.5 v squared. Let's see what we get from this. Do we need an exact value here by any chance? No. Okay, so what does this give us? 50 divided by 3 divided by 3.5 and then square root of that. That's giving me 2.182 from this. Velocity equals 2.182. If you want to round it off, you can write this as 2.18 meters per second. That's the final speed of these particles. Okay, so the work energy part was not that complicated here. The complicated part was basically this trigonometry that you had to use, okay, to find the change in height for them and how much is v traveled along the slope and how much has the height changed for both the particles, for both particles A and B. All right, so that's how it works. This is the final speed that we get from this. Make sense? Weight is only considered when you're using Newton's second law of motion. So let me actually show that to you as well. This is M1, work energy power. And yeah, should be here. Yeah. So remember these definitions. Forward force is any force that is acting in the direction of motion. So all forces that are acting in the same direction in which the particle is moving, that's a forward force. Driving force is all forward forces except weight or any component of weight. So all forward forces are considered driving forces as well, apart from weight. Weight is not considered a driving force. Okay. And similarly, backward force is any force that is opposing motion. Resistance is all backward forces apart from weight or any component of weight. So just weight is not considered in any of them. But apart from that, driving force is all forward forces and resistance is all backward forces except weight. All right. So weight is not considered in driving force or resistance, but weight is considered as a forward force or a backward force. Okay. I would not recommend doing more yearly papers right now. Revise your notes and revise all the papers that you've already done until now, right? So all questions that you've done until now, revise them, okay? So don't start a new yearly paper now. That can, if you end up struggling with that, that can make you lose confidence right now. That's the last thing that you want at this point. There's not much that you can do from this point onward to basically improve your understanding a lot. Now, if you're really struggling, then maybe yes, but if you're prepared well, then this last time, these last hours, like 18 hours or something that you have before exam, you should spend them in making sure that you do not forget everything that you've learned until now. And how would you do that? Revise everything in detail. Revise your notes thoroughly and revise all the questions that you've attempted. Go through, have a look at all the questions that you've attempted until now, both the topical questions and the yearly papers that you've done. Have a look at all of them. Try to figure out where you made mistakes, how you corrected them, and try to retain all of that stuff. Okay, I think that's what you should be doing right now. Yes, Jarif. June
Sir,
20.
Yeah, can you do the 2021 May June question 3 and 4? I tried looking in your YouTube, but it was not there. So just need help
Okay.
with that.
June 2021.
And sir, one
See.
more thing. If
Yeah.
while doing the question, if you can explain, like those scenarios when they ask you that they go at the same distance or like come together at a certain distance. So how do I like approach, like what's the thinking process in those type of questions?
Is this one of those questions as well? What you're asking about?
Yeah, it does has one of those questions.
Okay, so let's discuss it while we do it, okay?
Yes, sir.
So it'll be easier to do it that way. June 21, paper 4.1, right? This is the one.
Yes,
Okay,
sir.
questions 3 and 4 from this. Okay, this one.
Yes, sir.
Okay, it says three particles P, Q, and R of masses 0.1 kilogram, 0.2 kilograms, and 0.5 kilograms respectively. They are at rest in a straight line on a smooth horizontal plane. Particle P is projected towards Q at a speed of 5 meters per second. After P and Q collide, P rebounds with speed 1 meter per second. Find the speed of Q immediately after the collision with P. The first part is pretty straightforward, right?
Yeah, sir. There's no problem with the first part. The second part is little
Okay,
difficult.
so can you tell me the result from the first part?
1 second, sir. That's 3 meter per second.
Okay, so we can actually represent that here. So we have three particles. One is P, another is Q, and then we have R. What happens before the collision? So before collision, what information do we have? We know that P is projected towards Q at a speed of 5 meters per second. Q and R are at rest. Okay, so these are at rest. Now, after the collision, P rebounds with a speed of 1 meter per second. This is what happens after the first collision. And you have to find the speed of Q immediately after collision. So you found this. What's this? Let's call this VQ. You found that VQ equals
3 meter per second.
3 meters per second. Okay. So Q starts moving to the right at a speed of 3 meters per second after the second collision happens. Okay. Now it says Q collides with R. So now when Q is moving to the right at 3 meters per second, it collides with R. Immediately after the collision with Q, R begins to move with speed v meters per second. Given that there's no subsequent collision between P and Q, find the greatest possible value of V. Okay, let's think about this. So we've got the particle P. Let me just change the pen sizes here quickly. Okay, so what do we know about particle P after the first collision? It's moving at 1 meters per second to the left side. Okay, P is moving to the left at 1 meter per second. What do we know about Q? Q is moving to the right at 3 meters per second. And what about R? R is at rest. R is at 0 meter per second. This is what we know before the second collision. Now, after this collision, they are saying R begins to move with speed v. Now, which direction is R going to move in? It's going to move to the right, right? Because Q is hitting it from the left side. So R is supposed to move to the right. So R is moving at v meters per second to the right side. Now, what's the greatest possible value of V such that there is no subsequent collision between P and Q? Now, they want that P and Q do not collide again. Now, how can we make sure that P and Q do not have another collision? Think about it. If the speed of Q was after the second collision, if speed of Q was 2 meters per second to the left, what would happen? P is still moving at 1 meter per second to the left, right? Because there's no other collision with P at this point. So if Q starts to move at 2 meters per second, is there going to be a collision?
Yes, sir.
Yes, because it will catch up with P at some point, right? So there will be another collision. Okay. What if Q starts moving to the left at 0.5 meters per second? Is there going to be another collision?
No, sir.
No, because it will not be able to catch up with P. Okay. What if it was 1 meter per second? Will there be another collision?
No, sir.
No, because they have the same velocities. They will keep moving at the same velocity, at the same distance from each other. And Q will never catch up with P. They will have the same distance forever, right? This is the extreme point that we have, right? That they are, if the speed of Q was even slightly more than this, there would be another collision. So this is kind of the extreme value that Q can have. Because after this, there will be a collision. So what we do is we say, let's find the corresponding value for V that we get at this extreme value for Q. Can we figure that out? We know the mass of Q. The mass of Q is 0.2 kilograms. This is 0.2 kilograms. Mass of R is 0.5 kilograms. What do we get from this? Momentum before collision equals momentum after collision. Let's just apply that on Q and R. What's the momentum before collision? 0.2 into, so this was to the right. So 0.2 into 3 plus 0, the momentum of R. Momentum of Q after collision, that is 0.2 into minus 1 because it's moving to the left, right? Plus 0.5 into V. Yes.
Sir, how did you consider that it's going towards the left? Like why, like P and Q will also not collide if the particle P is moving towards the right direction, right? It will also not collide, right?
Yes, so we're considering the extreme case when it's just about to collide. Remember, just like those limiting equilibrium cases that we have in friction, we consider the extreme case that, okay, if a force was supposed, if the force ends up being slightly more than that value, the particle will start moving. It's in limiting equilibrium. So it's that limiting case when Q is just at that point, the velocity of Q is just at that point that even if it was slightly more than this, it would end up colliding. Since we're looking for the greatest possible value of V, we are considering the extreme case for Q, because if V is greater on the right side, to balance that, Q on the left side will also have to be greater because the momentum has to remain conserved. So what's the greatest value that we can have so that there's no other collision? What we do is we consider this extreme case for Q, that if it was slightly more than this to the left side, it would end up colliding. So we're considering that extreme case in this case. Does that make sense?
All right, sir.
So what do we get from this? 0.6 equals minus 0.2 equals 0.5 V, and that will give you something. You can see what that turns out to be. 0.8 over 0.5.
1.6.
That will be 1.6. So this is the greatest possible value of V. If V was even slightly greater than this, if V was, let's say, 2 meters per second, you see, the total momentum has to remain the same. It's 0.6. Left-hand side is fixed. If we make this V bigger, this minus 1 will have to be even smaller. That means minus 2, minus 1 point something. And that will make it collide with P. So the greater this value of V is, the greater this number is going to be on the left side. Make sense?
Yes, sir.
So this gives the greatest value of V. Okay. Then you have this question number 4.
Sir, the second part, the first part is easy. The second part, yeah.
Okay. Was it not there in the recording?
No, sir, it wasn't.
Okay. All right, let's think about this. It says 2 cyclists, Isabella and Maria, they are having a race. They both travel along a straight road with constant acceleration. So they're moving with constant acceleration, starting from rest at point A. Now, this first person, she accelerates for 5 seconds at a constant rate of A, then travels at the constant speed she has reached for 10 seconds before decelerating to rest at a constant rate over a period of 5 seconds. Okay, so constant speed is for 10 seconds, and then over a period of 5 seconds, she decelerates. Maria accelerates at a constant rate as well, reaching a speed of 5 meters per second in a distance of 27.5 meters. She then maintains this speed for a period of 10 seconds before decelerating to rest the constant rate over a period of 5 seconds. Okay, given that A equals 1.1, find which cyclist travels further. So you're done with the first part?
Yes, sir.
So you found the total distance traveled by both the particles, by both the cyclists, not the particles, right?
Yes, sir.
Okay, so now you're asked about find the value of A for which the 2 cyclists travel the same distance. Okay, so in the first part, we were given that A equals 1.1. Now we can't use that value of A. They're asking us to find a value for it at which the total distance is equal. So we need to find some expression for their total distance and equate their distance, right? If the total distance is supposed to be the same, we find their total distance traveled, an expression for that. That will be in terms of A, and then solve that equation to find the value of A. Does that make sense?
Can you please repeat, sir?
So they are saying the two cyclists travel the same distance. If they travel the same distance, what we can do is we can find their distance traveled in terms of A. Can we do that? Now, the thing is, most of this work you would have already done in the first part. It's just that you would have input the value of 1.1 there. So it's 2 marks because of that, because you could use some of the working that you've done in the first part already for this. But now, since we haven't done the first part, let me do it completely. So it says, since they travel the same distance, what we can do is we can find an expression for the total distance that they travel and then equate them. What's the total distance that they travel? Let's start with Isabella first. So she accelerates for 5 seconds at a constant rate of A meters per second squared. So that's how she is starting. Now, one way to think about this is through the graph, and that will make it much easier because you'll have some kind of a trapezium. You can find the area of that trapezium, or you can use constant acceleration formulas for each part separately, and it can also be done that way. Now, let me do it graphically. That will make things simpler. So let's talk about Isabella first. I'll actually just do this up there. So we have all the numbers in front. Let's talk about Isabella. How is she traveling? We know that she covers some distance at an acceleration of A for 5 seconds. We don't know how much acceleration this is. We do not know the gradient at this point. She then travels at the constant speed that she has reached for 10 seconds. So for the next 10 seconds, she continues at this constant speed until time equals 15. And then she decelerates at a constant rate over a period of 5 seconds. So let's say this is 20. She decelerates at that constant rate. Now you see, this gradient is supposed to be the same as this gradient, only the signs are going to be different. Because she's taking the same amount of time, 5 seconds, and the speeds are also the same, 0 to some value. Let's call this value V here. Let's say this is V.
Sir, V
Okay.
is 5.5.
V is
5.5.
5.5. How do we know that?
Sir, we use the formula V square is equal to U square plus 2AS. We know the initial is 0 and 2 into acceleration.
Acceleration is unknown.
Acceleration is 1.1, sir.
No, I'm doing the second part. I'm just showing that
okay.
here.
Sorry,
I'm doing the
sorry,
second
sorry.
part, okay? So acceleration is not known, okay? We don't know the acceleration. So this is A, let's say. Okay, so this is how Isabella travels. Now, what about the other person? She's traveling at a constant, she's accelerating at a constant rate, reaching a speed of 5 meters per second in a distance of 27.5 meters. So for the other person, we know in the first 5 seconds, she is traveling 27.5 seconds. This is V and this is T. She's accelerating at a constant rate. She then maintains the speed for a period of 10 seconds. She maintains the speed for the next 10 seconds. This is 15. And then she decelerates to rest over a period of 5 seconds. At 20 seconds, she comes back to rest. This is how the journey of the second person looks like. Now we know that this area is 27.5. Yes?
Sir, how did you know these acceleration is 5 seconds for Maria?
It says that over a period of 5 seconds. Okay, I'm sorry. You're right. This is not 5 seconds. It's the speed that's 5 times. Sorry. This should have been 5. And if this is 5, then we don't know what these values are as well. Okay. Now, since this is 27.5, can you find the value of time for this? Now, the thing is, you would have done most of this in the first part already, okay? So don't think that it's too much for 2 marks because you've done most of this work in the first part already. Now, how do you find this point? You can say area of this part, half into, let's call this t, half into t into 5. What would that be? 27.5. And because she travels a distance of 27.5 meters here, can we find this t value from this? What's this?
So I think it's 11.
11. So this point is actually supposed to be 11. If this is 11, and this is 21, and this is 26. Okay. Now, how much does Maria travels for this whole journey? Can we find the rest of the area? In fact, we can just find the total area directly here now. This is 10. This length is 10. This length is 26. Height is 5. Can we find the total distance traveled by Maria? Right?
Yes, sir.
So what would that be? Again, you would have calculated this already in the first part, right?
Yes, sir. That's 90 meters.
That's 90 meters. Area of trapezium, right? Half into 26 plus 10 whole multiplied by 5. And you're saying that gives you 90 meters. You've done this work in the first part already. Now you do the same thing for Isabella. Now, this is the information that you have for her. We know that the acceleration for the first part is a meters per second square. This acceleration is a meters per second square. Now, if we call this point 5 and v, what does that mean? That means v minus 0 over 5 minus 0, that should equal a. That's the gradient of this first part. Make sense? And that gives you v equal to 5 times a. The v value is supposed to be 5 times a. You can use that equation as well. V equals u plus at, right? You'll get 5a for that. Make sense?
All right, sir.
Now, once you've got this, now you can find the area of this trapezium as well. What's the area of this trapezium? Half into sum of parallel sides, that's 20 plus 10, multiplied by height. What's the height? Height is 5 times a. That equals 90. And that will give you the value for a.
Okay.
Make sense?
Okay. Yes, sir. Now it makes sense.
Now you've done this part already in the first part. And for the second part is, and in the first part, you've also done this. In fact, it's just that you're not inputting the value of a equal to 1.1 here. You just make this equation like this. Okay?
Okay, sir.
All right. Anything else?
No, that's it, sir. Thank you.
Okay. Okay, let me just do one last question and then we end for today then. This is November 18, paper 4.2. Okay, one last question and then we end. Okay. I'll be posting some other videos as well. I've already posted the difficult questions for kinematics, for forces in equilibrium, for kinematics with momentum, and also Newton's second law of motion from the recent papers. The most difficult questions that I found in the recent papers in the last 4 years. I'll be doing the same thing for work energy power in an hour or so as well. After once I'm done with this class, after that, I'll be posting that as well, inshallah. Okay, now let's have a look at this one last question before we end. Or in fact, maybe I can just focus on those last papers and just confirm if that person is still here. Asked about this. Okay, so if there are no other questions, I think we can just end this here. Just a reminder about what you need to take care of for tomorrow. Make sure that you sleep well, first of all, have a good night's sleep. And make sure that you do not get stuck at a question. It's happening a lot in recent papers. The last couple of years, there have been some papers which have been extremely long. Okay, and mostly the last question has been the longest one, but it's not necessary that it's always going to be the last question. So if you end up getting a very lengthy question in the middle, please make sure that you do not end up spending too much time on that. Okay, so if you can't figure, if it's a 3-4 mark part, 4-5 mark part, and you spend a few minutes in that, and you can't figure it, if you spend 4-5 minutes in that, and you can't figure out any direction for that, please make sure to move on right away. 1 hour 15 minutes, 75 minutes is not a very long time. Okay, it's not a very long time, and if you end up getting stuck at any one particular question, you can end up losing marks on potentially easier questions that may be there towards the end of the paper. Make sure to first do the easier questions, the easier parts. Then once you're sure that you're done with all of them, then get as many method marks as you can for questions that you can't quite figure out, but leave them for the very end. And that will make sure that everything else is taken care of by the threshold. Okay. 4 to March. Okay, so those of you who want to leave, by the way, you're free to leave. I will just have a look at a couple of other questions that people have posted here. As long as I'm not kicked out from my home. Let's see. Yeah, so you guys can leave if you want. Most of you have already left now. Let's have a look at just one question. March 23, 5B. I can show you that here, if that is solved. March 23. And then I'll do that one question. November 18, 4-2 that you're asking about. Is that what you're asking about? Yeah, so this is what it is. You can maybe take a screenshot of this. You take a screenshot of this if you want. In fact, this is something that I've covered in that forces and equilibrium video that I just posted as well. I've just posted, in fact, I posted that yesterday. Forces and equilibrium, difficult questions from that. I'm pretty sure this question is covered in that video. So if you want a full explanation of that, you will find that there. Okay. So let's just do that question that you're talking about. Let's have a look at that. Okay, November 18, paper 4-2. Question number 7 from this. Last question for today, and then we end. Yes. Okay, let's have a look at this quickly now. It says a particle of mass 0.3 kilograms is released from rest above a tank containing water. The particle falls vertically, taking 0.8 seconds to reach the water surface. Now, let's actually draw a diagram on the side so we don't have to read the full question statement again. So we have this tank, and this tank contains some water. Let's say it's full because we're only concerned about the particle hitting the surface of the water. Or yeah, this is the water in the container. The particle falls down from the top. It's released from rest. The mass of the particle is this. Let's say it's here. It gets released from this point. Just adjust the pen sizes quickly. Okay, so it's released from rest. It falls vertically, taking 0.8 seconds to reach the water surface. So it travels downwards. It takes 0.8 seconds. It was released from rest. Its initial velocity was 0 meters per second. There's no instantaneous change of speed when the particle enters the water. So whatever was the speed of the particle when it hit the water surface, it would be the same speed when it enters the water surface. The starting speed from this point onward will be the same as the final speed of the first part of the journey. So let's actually, so I often recommend labeling these points like this. You can say the point where it starts from, let's call that point A, and this point B where it hits the surface. Okay. Then when you're working, you can actually refer to these points, and that makes things easier to follow for the examiner as well. The depth of the water in the tank is 1.25 meters. So we know that this is 1.25 meters. The water exerts a force on the particle resisting its motion. Okay, so there's going to be some resistance while the particle is in water as well. So there's some resistance. The work done against resistance from the instant that the particle enters the water until it reaches the bottom of the tank is 1.2 joules. Work done against resistance. Use an energy method to find the speed of the particle when it reaches the bottom of the tank. Okay, so how do we use an energy method to find the speed of the particle at the bottom of the tank? Let's think about this. We could break it down into two parts if we wanted. Or we could think of doing this directly. Let's see if we can do it directly somehow. If that is going to work, change in kinetic energy, for that we'd have to find that because that is changing in the middle. Okay, let's break it down into two parts. Let's break it down into two parts from A to B and then from B to C. So what do we know from A to B first of all? From A to B, what information do we have? Let's use work done by driving force that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. Let's use this from A to B first of all. Now, what's the driving force? There's no driving force. It's the particle is just released from rest. This is 0. Change in kinetic energy, initial kinetic energy is 0. Final is what we do not know about. Let's call this VB, velocity at the point B. VB squared minus 0 squared. Plus change in potential energy. Do we know the change in potential energy? Mass of the particle was 0.3. So 0.3 into 10 into change in height. We do not know the change in height, do we? We do not know this change in height. So we would have to find that change in height. How do we do that? We can use the constant acceleration formulas for that. Plus the work done against resistance. That's also going to be 0 in this case. So for A to B part, let's actually use constant acceleration. Then we can use energy method for the second part. This is use constant acceleration because that's going to be much quicker. V equals U plus AT. Let's use this first of all to find the final velocity at that point. Initial speed is 0. It's moving downwards. Let's consider this as positive direction. U is 0. acceleration is going to be positive 10. Why? Because we're considering downwards positive. If downwards is positive, acceleration is also going to be positive. So that's 10 times t, that's 0.8. So I'm going to assume that the energy method that they've asked for is for the remaining part. For this part, let's just use this directly because that's going to give you the result directly. The final velocity here is 8 meters per second. Okay. At this point, at the point B, we know that the final velocity is 8 meters per second. Now, for the journey inside water, let's use the energy method from B to C. Let's call this bottom point C, the bottom of the container. Work done by driving force, that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. What's the work done by driving force? There's no driving force as such. Okay. So we say that's 0. Change in kinetic energy, we know the initial energy now. That was initial speed now, that was 8 meters per second. What's the final speed at the point C? Let's call that V. We say V squared minus 8 squared. That's the change in kinetic energy plus the change in potential energy. M is 0.3 into 10 into change in height, that is minus 1.25. Right? The height is reducing. So the change in height is negative, plus the work done against resistance. What's that? That's 1.2. And you can see what that turns out to be. What's the value of V that we get from this? Anyone? What value of V do we get from this? Where did my calculator go? What's the value of V that we get? My son has. Okay, I've lost my calculator. Apparently, my son has run away with it. Okay, so we find some final velocity from this. Okay, let me use it on my phone. Okay, so what has happened is my son has run away with my calculator. So well, that happens in class sometimes as well. Now, so it's 9. Okay, thank you so much for that. It's 9, so I'm going to assume that's correct. 9 meters per second. Okay, good. That's the first part. Okay, now it says when the particle reaches the bottom of the tank, it bounces back vertically upwards with initial speed 7 meters per second. As the particle rises through the water, it experiences a constant resistance of 1.8 Newton. The particle comes to instantaneous rest t seconds after it bounces on the bottom of the tank. Find the value of t. Now, how do we think about this? This is part 2 now. Now, when it hits the bottom of the surface, it bounces back vertically with initial speed of 7 meters per second. So now we know from the bottom of the tank, so inside this container, now let's consider this. Inside this container, it bounces back at a speed of 7 meters per second. As the particle rises through the water, it experiences a constant resistance force of 1.8 Newton. So think about this particle when it's moving upwards, it has a resistance. Resistance always opposes motion, right? So that is going to act in the downward direction. It experiences this resistance, 1.8 Newton. That's the resistance force acting downwards. The particle comes to instantaneous rest t seconds after it bounces on the bottom of the tank. So at some point, it's going to come to instantaneous rest here. So its velocity is going to be equal to 0 at that point. Find the value of t. Okay. Now, while the particle is in the water, what forces are acting on this particle? There is 1.8 Newton that's acting down in the downward direction. That's one force that's acting. What other force do we have? We've got weight of the particle. What was the weight of the particle? Weight of the particle was 3 Newton. That is also acting downwards. These are the two forces acting in the downward direction on this particle. Okay. What other forces do we have? Is there any other force apart from this? There's no other force apart from this. These are the only two forces acting in the downward direction. So all we have to do is use these two forces to find the acceleration that is acting on this particle. Can we find that? There's no upward force, right? So we can use resultant force equals mass into acceleration. Forward force equals mass into acceleration. What does that give us? Forward force is nothing. The particle is moving upwards. Downward force, backward forces, they are resistance. That's 1.8. And the weight, that is 3. That should equal mass of the particle. What's the mass of the particle? It's 0.3 into acceleration. So we can find the acceleration of the particle for this part of the journey. What's the acceleration? Again, I need some help with that. Let's figure this out. Minus 4.8 divided by 0.3. Acceleration turns out to be minus 16. So A value is minus 16. Okay. Calculator. A is minus 16. So I have my calculator back now. Finally. Okay. A equals minus 16. This is what we've got. Now, when the value of A is minus 16, what we have is that the initial velocity was 7, acceleration is minus 16, and the final velocity when the particle comes to instantaneous rest, what's that? The final velocity is 0, right? The final velocity is going to be equal to 0. So let's use this to find what we're looking for. We're looking for the time it takes from the bottom of the container to the top here. Let's see what that turns out to be. Acceleration is minus 16. U is 7. A is minus 16. What do we have to find out? The value for time. Okay, let's see what we get from this. V equals U plus AT. What does that turn out to be? V is 0. U is 7. Minus 16 times T. And that does not give you anything. Okay, this is not giving me a value for time. Initial velocity is 7. Acceleration is minus 16. It comes to rest instantaneously. T seconds after this. Okay, so it bounced on the bottom of the tank earlier at an initial speed of 7. It comes to instantaneous rest T seconds after it bounces on the bottom of the tank. So maybe we're not reading the question statement correctly. Initial speed we know is 7, and acceleration is minus 16. That's 1.25 meters. Oh. So the problem that's happening here is that it's not coming to rest. It's not coming to rest inside water. It's not coming to rest inside water. That's the problem that's happening here. We're not getting any time value for here because it does not come to rest at all inside water. The final velocity cannot be zero inside water. That's why we're not getting a value for t. Okay. The problem is we're not getting a value for t because this is the acceleration inside water. Inside water. When we put v equal to 0 here, we do not get any value for time. Why? Because inside water, its final velocity is not becoming 0. It's not becoming equal to 0. Okay? It's actually going to reach the surface and then go out. And then at some point, its velocity is going to become 0. Because inside the container, we're not getting any value for t corresponding to when velocity is 0. So what do we do then? We can't put v equal to 0 because that's not giving us any value of time. If we're not getting any value of time when v equals 0, that means it's not coming to an instantaneous test inside the container. That's not happening. So how do you find that total time taken then? We'll have to break the journey into two parts then. This is the container containing the water. You have two parts of this journey now. One from the bottom of the container, let's call this point A, and to the surface of the container, and then to the top. This is the bottom of the container. This is the surface of the container, and this is the maximum point. Okay. And now what you do is you find the time taken from X to Y, first of all. You have the time taken for this part of the journey. Now, what do we know for this part of the journey? What information do we have? We know the depth of the water in the container. What was the depth of the water? 1.25 meters. So what we do is we use that displacement 1.25 and find the time taken to go from X to Y. So first of all, we are considering this part of the journey. That's from X to Y. And we can find the time taken for this. Which equation connects these four things? S equals ut plus half at square. Let's input values in this. 1.25 equals 7 into t plus half into minus 16 into t squared. What do we get from this? 1.25 equals 7t minus 8t squared. 8t squared minus 7t plus 1.25 equal to 0. Just put these values in the quadratic formula and write down the answers. Minus into minus 7 plus minus square root of minus 7 whole squared minus 4 into 8 into 1.25 whole divided by 2 into 8. And that will give you some value for time. Let's see what this gives us. Let's see what this turns out to be. Eight minus 7, 1.25. That is giving me one value for time, which is 0.625. And then another value of time, which is 0.25. Okay, so I'm getting two values of time from this, 0.25 and 0.625. Okay. These are the two values of t that I'm getting from this. Now that means its displacement first becomes 1.25 when time is 0.25. So basically it's considering this journey, the journey like this, that it goes upwards and then it comes downwards. First of all, displacement becomes that much when time is 5. And then it becomes again, it becomes the same displacement again when time is equal to 0.625. We have to consider the first time instant when that happens. Okay, so we have to consider the first time instant when it reaches the surface. This is the first time. First instant when it reaches the surface. That's the value of time that we would use here. So it takes 0.25 seconds to reach the top of the container. So now it has reached this point Y, the top of the container. How much time did that take? That took 0.25 seconds. Now we have to consider the second part of the journey. The second part of the journey is from Y to Z, when finally its velocity becomes 0 at the top. Now we have to consider this part. Now what happens from Y to Z? For Y to Z part of the journey, let's see what information we have. Okay, let me check that. I'll get back to you in a moment. Y to Z, what do we know about Y to Z part of the journey? Y to Z part of the journey, that is giving me final velocity 0. That's one thing that we have. It's in the air now. What about acceleration? It will be -10. We're considering upwards positive because the particle is moving in the upwards direction. We're saying acceleration is therefore -10. What else do we know from Y to Z part of the journey? Nothing else. So we need some other information for Y to Z part of the journey. What other information can we find? We can find the velocity at the point Y. This is something that we often have to do when we break the journey into two parts. We have to find the velocity at this point where the particle moves from one part of the journey to the second part of the journey. So what's the velocity at the point Y? How do we find that? From X to Y, we can find the final velocity as well. V equals U plus AT. Initial velocity was 7. Final acceleration was -16. And time taken, now we know the time taken is 0.25. Can we find the final velocity at that point? It's 7 minus 16 into 0.25. That's 3 meters per second. This is the velocity at the point Y. So now we consider Y to Z part of the journey. In Y to Z part of the journey, now we know the initial velocity. The velocity at the point Y, that is 3 meters per second. So now we consider the time taken to go from Y to Z. Let's figure that out. Which equation do we use again? V equals U plus AT. What does that give us? 0 equals 3 minus 10 times t, and time from here turns out to be 3 over 10, which is 0.3. This is the time taken from Y to Z, okay? And that gives you the total time of the journey. What's the total time taken in this journey? 0.25 while it was inside the container, and then 0.3 more in the air, that is 0.55 seconds. That's the result that we get from this. Okay. All right, now let me answer your question. So we're saying, how do we know? How can we get a value of 7 over 16? How do you get 7 over 16 from that? So if you put V equal to 0, so yeah, so let's assume that V becomes 0 inside water. So we don't know that, right? So of course, yes, we don't know that in the exam, if that the value of V becomes 0 inside the container or outside the container. What do we know about X, Y part of the journey? We know U is 7. We know acceleration is -16. And we consider V equal to 0. How do you find T from that? How do you find T from that? Let's try finding this. V equals U plus AT. 0 equals 7 minus 16T. t equals 16 over 7. It's giving us 16 over 7, which is 2.285 seconds. 2.285 seconds. Okay, that's the time that we're getting from this. Now, if it takes 2.285 seconds, if you find the displacement covered for this, let's see what that turns out to be. S equals ut 7 into 2.285 7 into 2.285 7 into 2.285 plus half into a, which is minus 16 into 2.285 whole square. If you find the displacement from this, that will be more than 1.25. So that means inside the water, it's not becoming zero. Okay, inside the water, it's not becoming zero because this displacement turns out to be greater than 1.25. So that cannot happen inside the water. All right, I hope that makes sense. Now, I think we will have to end this here now because I'm getting called again and again for dinner. So I'll have to go. All the best for your exam now. Just make sure that you sleep well and also make sure that you time yourself well. Do the easier questions first. Okay. Don't get stuck in the middle. That's very important. Don't get stuck in the middle. If you find talked about this before as well, I'm going to just end this here. I'll see you again at another time. All the best for your exams. Allah Hafiz. Yeah, so he's the one who stole my calculator. So, okay. Allah Hafiz.